you. And so welcome back after lunch. And I'm just going to start sharing again. Okay, so just to recap where we got to, we had begun to talk about testing for a Bernoulli trials process. And I had done some forecasting in R, and we're going to have a look at the results. So this is what I'm going to do. I'm going to look at binomial test results. And then after that, I'm going to talk about, firstly, backtesting expected shortfall, and then talk about scoring functions for comparing VAR forecasts. So that's my intention. And here again is my R console in RStudio. So let me just make that as big as possible. Okay, so to go back to where we were, I had done some rolling forecasting, which you're looking at here. And you can see it's a gauge roll. There are 200 refits because although I'm making 1,000 forecasts, I'm refitting every 5 steps just for speed. And so I've made 1,000 forecasts with my model. The first model was the right model, although the parameters always had to be estimated. The dates are meaningless. So the dates are artificial dates because it was simulated data, so there are no rates. And this tells us some features of the forecast density, such as the volatility and the shape parameter, which is an estimate of the degree of freedom in the student, and also the realized values. And so the question is, how good are the VAR forecasts? And that's what the report tells us. So the report here tells us about the quality of the VAR forecasts. And so you can see that for the correct model here, we did 1,000 forecasts. We're estimating the 99% VAR. So it actually says here alpha 1%. Excuse me while I let my dog in. So it says alpha 1%. And so you would expect 10 exceptions. And in fact, miraculously, we get exactly 10% exceptions. So the actual percentage is 1%. The test, which is called unconditional coverage, and which is attributed to the author Kupiec, is just a binomial test, an unconditional binomial test. And the p-value is large, and we do not reject the null hypothesis, which is good because we are actually forecasting with the right model. The Christofferson test is the conditional test that I mentioned in the slides, and also we do not reject the null hypothesis. But let's have a look at the picture that goes with that. So that's the picture of the exceptions. And each of the red dots represents a day on which an exception takes place. So the actual realized loss is less than the estimated VAR. And so there will be 10 such dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what about the second method? So this was misspecified. It has the wrong distribution. And so if we look at that, well, actually, surprisingly, although it's using the wrong distribution, the number of VAR exceedances is still quite reasonable. In fact, it's actually smaller. It's 1 smaller. This is entirely possible because it is just a simulation. And so, although the model is incorrectly specified, the 2 tests also do not lead to rejection. So where it says reject null, this is the unconditional test. And this one here at the bottom that I've just highlighted is the conditional test. Neither are rejected. The conditional test is testing for Markovian dependence in the violations. And if we look at the picture, we'll see that it doesn't really look much different from the previous picture, except this time that there are 9 of the red dots. So the VAR exceptions don't tell us about the differences between these two models. The other tests we look at will. So the VAR test is really too weak here to detect that the modeling group is actually using the wrong kind of distribution in the model. And it is a distribution that will tend to lead to an underestimate of expected shortfall. The third group, well, here we do get bad results. So this group did not estimate value at risk. They have 28 VAR exceptions. They have 28, whereas 10 is what you would expect. And this is certainly sufficient to reject the null hypothesis in the unconditional test, and also it's rejected in the conditional test. And if you look at the picture, you'll see why. The estimate does not adapt to volatility, and in the periods here where there is quite a lot of volatility, there are multiple exceptions of the VAR leading to this result. So the next thing I'll look at is the spacings between them. So the spacings between them should be geometrically distributed. Moreover, the parameter of the geometric distribution should be, let me just check what I said before, it should be, the mean should be 1/1 minus alpha, the expected waiting time between exceptions. And so to implement this test, there is a little function. All of this is documented in the script that you've been given, the R Markdown script. And so I won't talk about actual programming, I'll just talk about concepts. So I'm going to use that function and look at the VAR spacings. And so you see a picture has just been formed here. Let's move that out of the way. So this picture here is a quantile plot again. You can see here we have quantiles of a geometric distribution, and here we have the actual spaces in days. And these points should line up on a straight line if the geometric model is a reasonable model. And moreover, there is a p-value, which is a Kolmogorov-Smirnov goodness of fit test, actually for the exponential distribution. You may wonder why so when this is carried out here, it's actually carried out here with a function called ks test, and it actually compares with the exponential. The Kolmogorov-Smirnov test is designed for continuous distributions. And so you can't put in the name of a discrete distribution like geometric. So the geometric takes positive integer values, whereas the exponential takes a continuum of positive values. So that's why. And anyway, so the first forecasting group passed the test. The p-value is large. The second forecasting group, they don't actually pass the test. This one gives a significant p-value. So this was the group that used the wrong distribution. They used a normal distribution. Now, you may have noted that in order to get a reasonable number of spacings, I dropped the value, or I increased the value to 0.05. So in other words, I'm actually looking at exceptions of the 95% quantile to carry out this test. So rather than the 99%, I'm looking at exceptions of the 95%. Because if I take 99%, I have very few data to work with, and I have rather weak tests. So for that reason, I took 95%. So the second group, it's rejected. The p-value is too small. You may recall that in statistics, there's a common rule of thumb that if your p-value is less than 5%, this is rejection. And for the third group, there is a very strong rejection. The p-value is tiny, and the points do not lie on on a straight line. That's quite clear from the picture. And so the spacings test actually detects, you could say, that the second and third groups are using a inferior model, and the first group passes the spacings test. Now, the next test to describe, and for that I will bring up my slides again, is expected shortfall. So one of the options that people have nowadays is to, so I mentioned that under fundamental review of the trading book, a bank must go beyond testing value at risk. And so they can, if they want, test expected shortfall estimates directly. And what happens here is we look at a different identification function. So for var, if I may go back, this is the identification function. It's a function such that the expected value of that function, and it's a function of the value at risk and the realized loss, conditional on past information, such that that is 0. Now, there is an identification function that you can use with expected shortfall, but it's difficult, if not impossible, to test expected shortfall without testing var 2. So in fact, the identification function is a function of the quantile estimate Q, the expected shortfall estimate at the same level, and the realized loss. And what it is you compare the loss with the expected shortfall. You divide by the expected shortfall to standardize it, and you multiply that by the indicator that the loss exceeds the quantile. That's the identification function, because by the definition of expected shortfall, the expected value of that must be 0. Okay, that's something that you might have to check if you go back to the definition of expected shortfall. It must hold that this function of the alpha var and the alpha expected shortfall and the loss, this must be 0 in expectation. So the idea is that we form a process of those values. Okay, so KT is a process of those values. And KT should be a process that has a mean of 0. It should have a mean of 0. Under some stronger model assumptions, it should actually be IID and mean 0. But it should always have a mean of 0 by the definition of the expected shortfall. And so what we do is we form something called violation residuals. We insert our estimates of var, we insert our estimates of expected shortfall, we insert the losses, and these give us residuals. And then we test whether they have a mean of 0. This can be done either with a t-test, which is what I'll do, or with a bootstrap hypothesis test, which I won't go into. But this is an idea that I actually developed myself with Rüdiger Frey 20 years ago in a paper in the Journal of Empirical Finance. And since then, it's a test that's been quite widely used, and it is incorporated in the Garch library in R, written by Alexios Galanos. So going back to the R, again, I've coded this test in a very short function. So what I've just highlighted in blue is the function that will do the test. But again, I'd just like to concentrate on what you get from this. So let us first take the first modeling group. So the first modeling group is using the correct modeling. And for them, what you see here, the picture is a picture of the violation residuals. So I'm looking at the 95% level because at the, I could do it at the 99% level. I'll show you the picture for that. That's the 99% level, but there's not really enough data to get a reliable test. So I will do it at the 95% level, where I have more exceptions of the var, and therefore I can calculate more of these expected shortfall residuals. And so the values are either 0 if the loss does not exceed the var, and if the loss does exceed the var, then the values are non-zero. But they should be zero in mean. They should have a mean of zero. And the red horizontal line shows you the empirical mean of the violation residuals. And so that shows you the empirical mean, and it's a bit smaller than zero. It's slightly smaller than zero, but the test shows you that this is not a significant difference. So the p-value here is bigger than 5%, and so the null hypothesis is not actually rejected here in this particular case. And so the first modeling group passes the expected shortfall test. And so let's move on to the so let's move on to the second group and have a look at their picture. So for the second group, there is a bigger discrepancy between the red line and zero. This is increased, and in fact, the decision this time is reject the null hypothesis. The p-value is now smaller than 5%, and so there is significant evidence that these residuals, these violation residuals, have a mean that is not zero. And therefore, the expected shortfall estimates are suspicious. They tend to be too small. That's the problem here. The mean is on the negative side, meaning that the estimates tend to be too small. And then for the third group, well, for the third group, it's also rejected. For the third group, you have these clusters of values which are non-zero because volatility is not being modeled. And the decision, again, the p-value is less than 5%. So we would typically reject the null hypothesis. So in other words, the expected shortfall test reveals the problems with the two false specifications in this particular case. But once again, we have to look at a lower var level in order to get enough data to carry out a test. So in order to get enough data to carry out the test, we look at a lower level of var. So I will now move on to the next testing idea. And this relates to a question that I answered before lunch. So yeah, so we've discussed, if you like, the plain vanilla tests of var, the unconditional binomial test of Kupiec and the Markov chain-based conditional test of Christofferson. We've discussed the test based on violation residuals for expected shortfall that I proposed with Rüdiger Frey. And we're now going to move into the third section of the second chapter. And in this section, what we will do is I will tell you about a concept called a listability and how this can be used to compare methods. So it's more of a comparative method. If you have two different ways of calculating your forecast distributions and your var estimates, and you want to know which is the more accurate way of getting var estimates, then the methods in this section are methods that one could think of using. And the ideas here were extremely popular and fashionable about 5 or 6 years ago in a series of papers. It was the listability concept in backtesting was first written about by Gneiting in 2011, and there are some other important papers that I've cited here. The references are all given in full at the end of the slides. So the key concept in this theory is a scoring function. And so the scoring function, it measures the difference between a forecast and a realized loss. So if Y is the forecast and L is the loss, S is the difference. And you want to minimize the score. If you're a forecaster, the idea of a scoring function is you want to have a small score because you are minimizing the discrepancy between forecast and actual loss. So the theory here is perhaps a little deeper than other things I've talked about up to now. So let us consider risk measures that can be calculated from a probability distribution. They're sometimes called law invariant risk measures. So let us consider them slightly more generally, and we will call them ρ at the moment. And these risk measures, they can be calculated from the distribution function of the loss f. So we will consider them as functionals, t of the loss. And the idea of a listability is we look for a situation, we look for a scoring function for a class of loss distributions such that a particular functional of the loss distribution minimizes the score. So this is the formula 9 we should look at carefully. So what we're taking is the expected value of a scoring function with respect to the distribution of the loss. So the expected value of S with respect to the distribution of the loss, which can be written as an integral of the scoring function over the distribution of the loss. And we're going to suppose that this expected score can be minimized by a functional of the distribution function. So something we can calculate from the distribution function. So let us suppose that this functional minimizes the expected score for some scoring function and for any loss distribution in let's say a large class of loss distributions. Now, if that is the case, let's make one further assumption. Let's assume that TF is the unique functional which minimizes formula 9. If that's the case, the scoring function is said to be strictly consistent for the functional, and the functional is said to be an elicitable functional, or in our language, an elicitable risk measure. Okay, so an elicitable risk measure is a functional of the loss distribution which minimizes a scoring problem. And to jump forward one slide, value at risk is an elicitable risk measure. It's a functional of the loss distribution. It is in fact the quantile, and it does minimize a particular scoring function. If you've heard about quantile regression, in fact, it's the scoring function in quantile regression. One side remark I will make at this point is that from this framework, you can actually get identification functions, because if 9 holds, if formula 9 holds for some functional t and for some scoring function s, then by taking a derivative under the integral, you can see that you are led to a function h whose expectation is 0. That function h is the derivative of the scoring function. And so you can get identification functions for hypothesis testing. You can actually get them from consistent scoring functions. So there is a connection there. But that's a small point, which I won't dwell on. What I do want to say is what happens with VAR. The VAR risk measure is elicible. The functional is the quantile function. And the scoring function, which is strictly consistent for the quantile function, is given here. What we do is we take the absolute difference between the loss and the forecast. So L is the realized loss, Y is the forecast. And we multiply that by the absolute difference between the indicator that the loss is less than the forecast minus alpha. So this may look, number 10 may look like quite a strange object, but in fact, it's what is used in quantile regression, if you've ever come across that idea in econometrics. And we're going to use it now to evaluate our VAR forecasting methodology. So maybe jumping over the second point and going to the final point. The expected shortfall is not an elistable functional of a loss distribution. So it has been shown that although VAR is an elistable functional, so there is a scoring function that will work, there is no scoring function for expected shortfall. So expected shortfall, to read the last thing on this slide, is actually not elistable. There is another risk measure that academics got quite interested in, which was something called the expectile. And the expectile is the only risk measure that is elistable and also has a set of axioms known as the axioms of coherence that are sometimes considered desirable for risk measures. And so I will mention in passing that there is another risk measure, it's called the alpha expectile. And what it is, it's the functional of a distribution function that minimizes this scoring function, which is exactly the same as the last one, except that there is a power of 2 on the second term. If you take this second term and you raise it to the power 2, you get this scoring function, and this is minimized by the expectile. In fact, that's the way that the expectile is defined. And so therefore, that's also an elistable risk measure. And there's a bit of literature about it, but I won't use that any further. Instead, what I'm going to do is in this slide, which will complete this second section, I'm going to attempt to compute VAR scores for my prediction methods. And so what I do is, if you look at the form of the scoring function, where shall we find it? Here. So the scoring function is a function of the discrepancy between the forecast and the realized loss. So the forecast that goes into the scoring function, if I go here, the forecast that goes into the scoring function is the VAR. And here is the loss. And the scoring function that I take is the one that I mentioned before, which is the scoring function for value at risk. And I can compute that every day. I have a 1,000-day backtest. So for every one of 1,000 days, I can compute that score. And then I can work out the average score. And the idea is that the model which gives the best average score is probably the best model for estimating quantiles. Okay, if it gives the lowest average score, then relative to other models that give higher scores, it should be a better model for estimating alpha quantiles or the alpha value at risk. So if I have two models A and B, and the first delivers VAR estimates VAR A, and the second gives you VAR B, and this corresponding scores or average scores are QA and QB, then what we expect is that the better model from the point of view of VAR estimation should be the one that gives the smaller value for Q. Of course, we need enough data. It's not certain that this will happen, but I'm going to go back to the script now, and I'm going to run the VAR score test. So this is actually a very small function that I've written here. This is a function to calculate VAR scores. And the main part of it, if you're able to code in R, you probably see that the main part of it here is precisely that function that I've been talking about, which is given here in formula 10. So that's basically formula 10. So I'll define that function, and we'll compute the VAR scores for each method. And this is what you find. The VAR score for method 1 is the smallest, which is reassuring because it is the method 1 is the true model. That's the group, the forecasting group who are using the true model. So they get a score of 163. Whereas the forecasting group that is using the right kind of stochastic process, the right kind of time series model, but the wrong distribution, they get a larger VAR score. It's not that much larger, but it is larger. And the ones who aren't bothering to model the dynamics of the data, they're just fitting a distribution, they get a pretty terrible VAR score. So this provides, the great thing here about a simulation is we know which is the correct model. And so we know we can evaluate whether these kinds of tests are giving us the right kind of information. So that's a comparative test. And here, so the idea of VAR scoring, just to repeat myself, there is no comparable expected shortfall scoring test. So that works for VAR. For expected shortfall, we were using a test based on the idea of these violation residuals. Right. We're into the final hour, including questions. It's 2 o'clock, and that's about where I was hoping to be at this point. I've covered here what I would consider to be basic is probably the wrong word, but more fundamental methods: VAR backtesting, expected shortfall backtesting, and the VAR scoring, which has been quite popular more recently. But what I want to cover in the final section is some new methods, and I want to tell you about pit values. And I also want to, I was taken at the beginning in the introduction by the comments, I think it was by Jose, about the importance of technology in finance and banking in the future. So with that in mind, I thought I would show you a nice tool for running simulation studies, which is very helpful for evaluating testing methodology. And so I hope to show you a couple of other nice things using R. So what does PIT mean? So now we're going to talk about, let's make this a bit bigger. We're going to talk about PIT values and methods that use them. And so first of all, I should tell you what PIT means. So PIT stands for Probability Integral Transform. And that is quite a mathematical term, but the concept is quite simple. So increasingly, regulators are being given more data than simply VAR exceedances. And in America, they've been collecting PIT data for quite a long time. And the reason I became interested was that I was approached by someone working with the US regulator, Michael Gordy, who said they had PIT data for the major US banks from backtesting. And could we look at ways of getting powerful tests that exploit PIT data? And so what is a PIT? So the PIT, I'll call it PT, the PIT, but it's the value you get if you take the forecast distribution and you apply it to the realized loss. So the forecast distribution is what you make based on information up to time t-1 in order to forecast value at risks for time t. But then at time t, you observe the realized loss. And if you apply the forecast distribution that you designed one step before, if you apply it to the loss, the value you get is the PIT. And the nice thing about the PITs is, in fact, they tell you about VAR exceptions or VAR exceedances at every level alpha. So if a PIT is greater or equal to alpha, that is actually mathematically equivalent to saying that the loss is greater than or equal to the alpha VAR, the estimated alpha VAR. So the PIT is made using the estimated distribution and the VAR is calculated from the estimated distribution. Now, if a forecaster was an oracle, so the ideal forecaster is the forecaster who is miraculously able to guess the true model every time. So if the models used coincided with the true distributions, then the operation of applying ft is known as the probability integral transform, because you're transforming a random variable with its own distribution. So you're transforming LT with its own distribution, and this gives you a uniform random variable. In fact, it's more powerful than that. If the FT hats are the true distributions, then the process of pit values is independent, identically distributed, and uniform. And this is often called the Rosenblatt transformation. So it works in general. I don't have to assume anything about stationary time series or anything like that. It works in general that if I transform the losses with their own true conditional loss distributions, then I get IID uniform variables. And so the idea is that we compute pits and we test them for uniformity. And not only for uniformity, but we test them for independence. And in America, for banks that have internal model approval, they have had to report their pits since 2013. And that's the data which we looked at in a paper which is in the Journal of Banking and Finance, and which is in the references at the end of this talk. And the question we addressed is, well, if you have the pits, what's the best way of exploiting this additional information? And to make things just a little bit more transparent, this is what the data might look like. So here are 8 days, and you might make a forecast for day 1. And from that forecast, you might compute the VAR. And then at the end of day 1, there is a realized loss. And of course, we can always look to see whether the realized loss exceeds the VAR. It doesn't on day 1. But the pit is what you get when you apply the distribution function with which you computed the quantile. You apply the distribution function to the realized loss, and you get the pit. And you do this every day, and you get a pit every day. And what you can see is that this relates to the 99% VAR. So there's only one day on which the actual loss, which is about 2.96. So there's one day on which the actual loss exceeds the VAR. So that is a VAR exceedance. That's the only day. But moreover, the pit on that day is bigger than 0.99. So we could also, without looking at the VAR, we can also tell that day 5 is an exceedance because the pit is bigger than 99%. And we can tell, for example, that on day 8, the loss exceeded the 80% VAR. So because the pit is bigger than 80%, the loss on this day actually exceeded the 80% VAR. So the pits tell us about exceedances of different VAR levels. So that's the data we have. Now, the idea of using the pit transform for evaluating forecasts or forecast distributions is not a new one. So there's a well-known paper by Diebold from 1998, which is about how you evaluate forecast densities using pit values by testing for independence and uniformity. So we always go back to this idea of Rosenblatt that these pits should be IID uniform, meaning uniform on the interval 0, 1. So Diebold knew that, but what we are doing in our paper, so this is our paper here, McNeil and Gordy, what we are doing is we are prioritizing certain quantiles, because in risk management, some quantiles of the forecast distribution are more important than others. And you could say that accuracy in the good tail of high profits is much less important than accuracy in the bad tail of large losses. So we prioritize accuracy in the bad tail of large losses, that is high pit values. And what we do is we propose tests in which the exceedances of the threshold are weighted by a function of the probability level. So the test statistic weights exceedances by a function of the probability level. And the function which does the weighting is called the kernel function, and it makes our priorities for performance explicit in a way that I will attempt to explain. Okay, so let me move on to a definition of the spectral test. Actually, yeah, now I'll just wondering when to show you the next bit of R, whether to do it now or whether to. Yeah, I think I'll talk a little bit more about the slides, and then we'll move back to R. So spectral backtests. So the formula here basically explains the transformation that we use. So we make transformations of the indicator function for pit exceedances of different levels. So what do I mean by that? This is the event that a pit exceeds the level U, and this is the indicator of that event. And if we consider a whole series of level U's, but we weight them using a distribution. So in fact, nu here is a probability measure. More generally, it can be a Lebesgue-Stieltjes measure, but you can think of it just as a probability distribution. And we weight the different levels using this probability distribution. And we look at all possible levels between 0 and 1 and apply this weighting scheme. And we call that WT. W can be thought of as standing for weight. So what you get, in fact, this integral is quite simple. It is really just the measure of the interval from 0 to pt. So if you take the interval consisting of the closed interval from 0 to pt, it's really just the measure of that interval. But if we write it this way, you can see that what we're trying to do is to weight the indicator function. So WT increases in PT. That's clear from this, that as PT gets bigger, WT gets bigger. And you can think of it as a weighted pit. And we choose the measure such that we are applying weight in the region of the usual value at risk level. So usually the var level is alpha equals 0.99. So the idea is this nu here will apply weight to levels which are close to 0.99. And the measure that does the weighting is called in our paper the kernel measure for the transform. And the kernel measure is non-zero in a certain set. So the support of the measure, so the set on which the measure is positive, that describes the subsets of the unit interval that are weighted. And there are basically two things we look at. One is we look at measures which are concentrated on points, so discrete measures, and the other is we look at measures on sub-intervals of the unit interval. So this may sound a bit mathematical, but the actual concept is not so difficult, and I will be showing you how it works in practice. So for every day t, we have a pit. So every day t, we have a pit, as in, sorry, I'm jumping around a bit, but think of these data. We have these data here, the pits, for American banks in our paper. And for every day, we can compute a weighted pit. And so we get a data set W1 to Wn. If we have 1,000 days, we have 1,000 weighted pits. And what we call a univariate spectral backtest is simply based on those weighted pits. We do have multivariate tests in which we look at different measures. So imagine that we took different probability measures, mu1 or nu1 up to nu j, so we have j of them, and we applied each of these in turn to the pit pt, and we called the result wtj. Then we would have, on every day, we'd have a vector of values of length j. And when we do that, we get multivariate tests, which are carried out on vectors. Now, what are we going to test for? We want that the pits are uniform. So what we're going to test is that the distribution of the weighted pits corresponds exactly to what it should do if the pits are uniform. So FW0, that means the distribution function of the weighted pits when the pits are uniform. And we want to test that the weighted pits really do have that distribution. You can think of it as simply testing for uniformity, but we're testing for uniformity in such a way that we prioritize or we weight certain quantiles more than others. And then the other thing we want to test is that the weighted pits are independent of the past. This is the mathematical symbol for independent. And we want to test independence of the weighted pits from the past. And that's what we'd like to do in general. We'd like to test hypothesis 12, but as before, some of the tests we use are unconditional and some are conditional. If it's unconditional, it's really just a test for the correct distribution. And if it's conditional, it's a test for both the correct distribution and the independence. And so this is going to generalize the VAR backtesting. This, in fact, will be a generalization of the VAR backtesting. So testing for uniformity. The kind of tests we use, and I think this is probably the end of the more technical slides. So the kind of tests we use, the univariate and the multivariate spectral tests, it depends on which case we're in. But they always use asymptotic normality. And this actually works remarkably well for the data samples that we've looked at. So they're called Z tests because they are based on the central limit theorem and asymptotic normality. We basically look at the average of these weighted pits, and under the null hypothesis, we can compute what is the true mean, what is the true variance, and we can therefore use the central limit theorem to conclude that a certain statistic should converge to normal. So the average weighted pit minus the expected value under the null divided by the variance scaled by the square root of n. This should converge to standard normal. In the multivariate tests, we look for convergence to chi-squared. The format is actually very much the same. We compare the weighted pits to their mean values, so that's just the same as that. But because we have vector observations, instead of dividing by a standard deviation, we multiply by the inverse of a covariance matrix, which we can calculate under the null hypothesis, and then we post-multiply by the same difference, and this should converge to chi-squared. So our tests are either based on a normal distribution or a chi-squared distribution, but in either case, they're based on asymptotic normality. Now that's quite a lot of theory. So I'd like to go into R for a bit now and set up the tests. So I put this in a second file, and I'll need a couple of libraries for this. I will need the spectral backtest library, which is not on CRAN, but is on it's accessible, publicly accessible, and there are instructions in the file here. In fact, I'll just show those instructions. I'll just compile again the HTML file and then show you where to get these. So this is what we're looking at. We're now in the second half of this. And actually the instructions at the top. The instructions at the top. So the library spectral backtest and also a library called TS Coppola, those ones are not at CRAN. Those ones you have to get from these links here, but they are publicly available. And so spectral backtest is one that Michael Gordy has written for our testing with colleagues at the Federal Reserve, and T.S. Coppola is something that I'll get to shortly and also talk about next week. Okay, so I want those libraries. So uniform distributions, I just want to make a couple of observations about a uniform distribution. What I'm going to do now is I'm going to generate data from a uniform distribution and a non-uniform distribution. And I'll tell you what I've done. So this command, number 9, this generates uniform data. And again, I'm going to control the situation so that I know what the truth is and so that I can see how well these tests perform. So pit 1, these are uniform data. And if I were to draw a histogram, which I'll just type in down here, you get something like this. The bar heights should be roughly similar because the values are uniformly distributed between 0 and 1. But I'm going to generate a second set of data which are nearly uniform, but not quite. And I do that by taking a beta distribution. So a beta distribution will also give me points on the unit interval. And if I draw a histogram like that, then at first glance, it looks fairly similar. This still looks quite uniform, but in fact, the distribution is no longer uniform because by choosing a parameter 0.9, and I've chosen the same parameter for both values of the beta distribution. Incidentally, if you wonder what a beta distribution is, we can always get help for many of these commands. Beta is the beta distribution, a distribution on the unit interval. And I pick the parameter to be 0.9. If I set the parameter to be 1, that is a uniform. A uniform is a special case of beta when the parameter is 1. But I've picked a value that is not quite 1. And so my histogram here is not quite uniform. And if I was a risk modeling group using the wrong forecast model to forecast my losses, my pits would be not uniform. They might be close to uniform, but they would be not perfectly uniform. And so what I'm trying to do is I'm trying to test for uniformity, but I want to do it in such a way that I prioritize certain quantiles. And that's why I will use the spectral test. And now let me go back and explain which kernels I'm going to use. So all my tests will follow the pattern on this slide. They will be Z tests, but I have to pick the kernel. So the key thing is I have to pick the kernel. And I'm going to look at 3 cases. This is not as difficult as it may look. The first case I will call the Dirac kernel. So if I choose a measure which is just point mass at the level alpha, then the spectral test or the spectral transformation just gives me the var exceedance indicator, because if you look at the construction, so this is the key construction here. If I pick nu to be, beg your pardon, if I pick nu here to be the Dirac measure at alpha, all I get is the indicator that the pit is bigger than or equal to alpha. And so this case takes me back into the case of var exceedances. And so the tests that I get in this case are basically tests of var exceedances. The WT are under the null hypothesis are IID Bernoulli, as we discussed before. And the Z test is that you get, so this Z test here, based on this idea, the Z test is a binomial score test, which I wrote about in a paper with Marie Kratz, which is also in the Journal of Banking and Finance. It is similar to the Kupiec test, which is the one that I used before, but I think it has a slightly better size for the same level of power. I'll come to size and power shortly. So that's the first idea. So all this means is that var backtesting is embedded in this framework. But what is interesting is to take more interesting measures. So instead of taking point mass at a single level, I could take point mass at m different levels. So I could place a point mass at alpha 1, alpha 2 to alpha m, and I could do that m times. And I could get, in that case, a weighted pit which takes this form. And in fact, WT follows a multinomial distribution. That's what formula 13 says. So whereas in the first case, it follows a Bernoulli distribution, in this case, it follows a multinomial distribution. We don't need to go into that, but this is a new test. So this is a new test in this framework and one that I'll use. All of these are discrete. So in every case here, the kernel is discrete. It's concentrated on points. Another possibility is that I take not one kernel, but I take m different kernels, all of which are Dirac. So I take delta alpha 1 and delta alpha m for a series of different values. And this gives me a multivariate test based on the indicators of level exceedances for different levels. And in fact, the Z test is exactly the same as Pearson's celebrated chi-squared test, which is well over 100 years old. And this has been used in backtesting in a paper by Campbell. So you get Pearson's chi-squared test. But you don't need to have a discrete kernel. You can have a continuous kernel. So in the continuous kernel case, you have a density. So you have a density GU, which is a non-negative function on 0, 1. And the ones that we look at are concentrated on windows. So we pick a window. This is not the window of data in backtesting, but the window of quantile levels. So we might say we're going to look at the performance between the 95th percentile and the 99.5 percentile, or something like that. In fact, that's what I'm going to do in the script. I'm going to pick exactly that window. So alpha 1 will be 0.95, alpha 2 will be 0.995. And then we specify, sorry, I clicked on the wrong link, but it's probably easiest to go back this way. Yeah. So then we need a function which is concentrated on that window. And there are a number of possibilities. You can have linear functions, you can have constant functions, you can have exponential functions. There are papers recently by Constantino and Curran and Du and Scanciano, where they use a uniform density on the interval alpha 1, alpha 2, but one can do other things as well. If one looks at a single kernel measure, it's a univariate test, but we'll also look at ones which involve two measures. We call them bispectral tests. And I'll come back to why bispectral can be interesting shortly. And the final ones we'll look at, so we will also consider one test which is strictly speaking neither discrete nor continuous, because it actually has a measure which has a discrete and a continuous part. So it's a mixed kernel. But I really just want to give a sense of ideas. So I won't say anything more about the mathematics of that kernel. I'll refer you to the paper. But I have a variety of kernels, and now we're going to set them up in R and use them in backtesting. So I'm going to pick a kernel window. And so, like I said, I'll take the quantile levels between 0.95 and 0.995. So I'm going to run those two lines. And then the way that the library works, you have to set up the kernel. So the first one I'll do is a binomial kernel or a Dirac kernel. I could call this one Dirac. The type mono means that it's just a single measure. And the nu is a discrete measure. And it is supported on the point 0.99. So this kernel, which is specified in this way, will give me a binomial test. So I set that one up. This one, Z3P, just to show you, that one gives this test here. So M is 3, okay, so M will be 3, and these weights K will be the values 0.25 on the first point, 0.5 on the second, and 0.25 on the third. The first point will be at alpha 1. The middle point will be at 0.99, and the third point will be at 0.995. So I set that one up. The third kernel is Pearson's test, the Pearson chi-squared test, which is, so I'll keep jumping backwards and forwards. That's this idea here, the Pearson test. So I'm going to take that one, again with 3 different values for alpha. Then I'm going to take a test which has a continuous measure. I'm going to call it uniform, and the measure will be uniform and continuous between the 2 values alpha 1 and alpha 2. So in fact, this test, which I now define, this test will be the same as the test used by these authors in recent papers, or at least papers in the last 6 or 7 years. As a contrast to having a uniform function, so in contrast to a uniform, I'm going to pick one which has a linear increasing function with slope 1. So that's this one. And then finally, I'm going to define 2 further kernels, ZLL and ZPNS. Both of these are bivariate, so they're both bivariate. The first uses a one kernel which corresponds to a linearly increasing density, and another which corresponds to a linearly decreasing. That's called ZLL, so linear. And the final test is actually a mixed kernel. So it's not possible to understand what all the details I'm talking about here, but all I want you to understand is that I have different kernels. I have 6 of them, I think. 1, 2, 3, 4, 5, 6. Actually, I have 7 of them. I have 7 different kernels, and I can put them in a list like this. And the function to carry out a spectral Z test, I'll just bring it up, spectral Z test, is here. So this is in the library Spectral Backtest, written by Michael Gordy at the Federal Reserve. And what we do is we take the name of the kernel, so this one is the binomial, and we take the pit values. So that's all it takes. We take the kernel and we take the pit values. And let's do the binomial one for the first data. The first data are truly uniform. This is the p-value, which is not significant. We say that less than 5% is significant. And this is the p-value for the Pearson test. It's also not significant. Now, the thing is that we're actually interested in applying all of these tests. And one way of doing that, so suppose we want to apply every single test that I've just defined. We can take this list here and we can apply the spectral Z test to every element of the list using a function called lapply. So when I run this, what you're going to see is for every test, binomial, Z3 point, Pearson, uniform spectrum, linear increasing spectrum, 2 spectra, linear increasing and decreasing, and another 2 spectra test, you get a p-value for all of them. But these are not all that interesting because it's just one data set. If I try it for, suppose I try it for the non-uniform data. So pit 2, these are non-uniform data. So what I do here is I try it for non-uniform data. These p-values are smaller, but not significant either. Only that one is close to significant. The others are smaller p-values, but they are not significant. And so in this case, none of these tests picked up the non-uniformity. But in order to work out whether they can pick up non-uniformity, we need to repeat this. We can't just do it once. We need to repeat it. And so the next thing I'm going to do is I'm going to show you how to create a simulation study to do this kind of thing. But before that, let me just say a little bit more about how these kernels work. So we have discrete ones, we have continuous ones. These are the ones that I'm looking at. This is a summary. So bin, Z3P, Pearson 3, ZU, ZLP, etc. The details are in the paper, but they all work slightly differently. The concept is the same. And we can get an idea of what's happening in this picture. I've picked out certain of these kernels. If the x-axis is the pits, so if the x-axis is the pits, and in this case, this picture is actually from the paper, the kernel window is slightly different. Here it's 0.985 to 0.995 instead of 0.95 to 0.995. So it's not as long. But what happens if we take for example, the 3-point kernel, which is this one here, then the pit values, the weighted pit values are 0 up to 0.985. Then they step up to 1/4, and then they step up to 3/4, and then they step up to 1 at 0.995. Whereas the continuous ones, the uniform kernel is just a straight line, which goes from 0 to 1, whereas the linearly increasing is this, this red line, and the linearly decreasing is this green line. So that's just the transformation that we're using. And the bin transformation would be if we have just a single step. So if we just had the indicator function for alpha bigger than 0.99, so there would be a single step up at 0.99. If you like, var backtesting is just based on a single indicator, whereas what we're doing here is we're allowing more complicated behavior on a window or on a set of points. And why are we doing this? Well, if we want to find out if the pits are uniform. And if the pits are uniform, then if we plotted the empirical distribution function, the empirical distribution function should be close to the straight line here, which is the line y equals x. But what we find in practice is that we can have situations where the risk group underestimates they underestimate quantiles, or where they overestimate quantiles. And so if we looked in a window between, here again, it's between 0.95 and 0.995, then, so we have cases here of over and underestimation, the red case and the green case, but we also have cases where there is overestimation on one side, overestimation on one side of the interval and underestimation on the other side of the interval. In fact, the tests with more than one kernel are very good at picking up what we call crossing, whereas the ones with a single kernel are quite effective in the red case and the green case. The ones with two kernels are particularly effective when there's a crossing pattern. Okay, so we're at the final topic, but I want to run the R code, which shows you how these tests perform. So we have a library called Simsalapar, which is a very clever library for doing simulation studies. And when you're testing methodology, I think there's nothing more valuable than a simulation study to work out how something works. And what we're going to do is, instead of generating one data set, we're going to generate 200. That will run relatively quickly. So we're going to generate 200 data sets. We're going to look at the case where the data are of size either 750, which is about 3 years of trading data, or 1,000, which is 4 years. We're going to look at the case where the pits are uniform and the case where the pits are non-uniform. So in fact, we're going to take these two models here, this one and this one, but we're just going to repeat this 200 times, this simulation. And we're going to use all of the kernels in the kernel list. And so what you have here is the way that such a study is specified. It's specified with a command called varlist, and you have to give it all the dimensions of the simulation study. So you have to, and you put these dimensions into a grid. So wherever it says type is grid, that means we're going to look at all possible values of n. We're going to look at all possible values of the distribution, which is either uniform or non-uniform, and all possible values of the kernel. Where it says frozen, that parameter is fixed. It won't change. But the ones in the grid are going to change. So we set up a simulation, and this gives a summary of what we've done in our simulation. We've set up the number of simulations, and we've set up a grid for n, the distribution and the kernel. The other element we need to be able to evaluate a test with one particular data set. So the only other thing that you have to write to do a simulation, you write the variable list. The only other thing you have to write is called a do1. So that's a do1. And a do1 takes one value of n, one value of the distribution, one value of the kernel, and any extra parameters that are needed, and it does the test once. So the do1 is defined. And what I've done here, I've taken 1,000 data, a non-uniform distribution, the binomial kernel. I don't actually need that parameter for the binomial. Oh, no, I do, because it's a non-uniform distribution. So that's actually the parameter of the beta, and that's the p-value. But what now happens is we do a full simulation study. So do lapply basically uses the function I used earlier, lapply, but it uses it in a simulation study. And I'm going to press the run button because this will take a, I don't know, minute or so. But I'm not using parallelization. So if we have a look at the library here, this can be made to run much faster if one has the time and if one has multiple cores. Like I say, I'm just using my home computer here. But this is the package, simulation studies. I'm not using parallelization, but it's possible. And there's what I'm using here. There are various functions for iterating over subjobs. So there are actually 6 different possibilities, each one of which will run a simulation study in a slightly different way. And I'm using the simplest one of all and waiting for some results to appear. We could, in the interest of time, I'm going to speak for another 7 or 8 minutes, I think, and then there'll be time for questions. So I have my eye on the clock. So
we have 15 minutes more than 16. Then you can stop when you want. Don't worry.
Okay, maybe I'll take just, I don't want to overrun. But maybe I will take just a little bit longer then to finish some of these details. And we can, I'm expecting that, oh, it's completed. I was wondering why that was taking so long, but the simulation has completed. And it looks a little bit complicated, but hopefully if you were to look in this here, you would see that I explain things in a bit more detail here if you wanted to reproduce it. So in here, you'll see a bit more detail about how you conduct the simulation study, conducting simulation study, and a bit more detail about what happens in these different commands. But what I want to do, I want to show you what results I get. So basically, I get a whole series of results here. The number is always the number of the simulation. So what I'm looking at here, if I just pick one, I'm looking at simulation 33, when the kernel is Pearson, when the distribution is either uniform or non-uniform, and when the sample size is either 750 or 150. And I get a p-value for every case. So every number here corresponds to a simulation, a kernel, a distribution, and a size, and I get a p-value. And I want to pick the p-values that are significant. So I do need to write a little function, a single function here to work out which p-values are significant. And then I can tabulate the results. So I've written a little function called rejection rate, which basically just takes the results from the simulation study and works out which ones are rejected and which ones aren't rejected. Then for my table, I'm going to put distribution and n into the row, and I'm going to put kernel into the column. You'll see what I mean. So I get a table like this. So you see that for the columns, I have the kernels. There are 7 of them. And for the rows, I have the distribution and I have the n, the sample size. And what you see here, the top panel is about size, because we would like tests which have size 5%. That's how we're defining them. We're saying that it's a reject if the p-value is less than 5%. And so we would like that the number of times that we reject the null hypothesis when it's actually true is 5%. And these numbers here are expressed as a percentage. So these numbers can be read as percentages. So what does it mean? It means that, let's take a value. Let's take, I don't know, let's take this one here. When the data really are uniform, the sample size is 750 and the test is Pearson, 3.5% of the time we reject, which is a little bit low for a size 5% test. It should be as close to 5 as possible. But this is only based on 200 replications. And really, we should do 1,000. We just have to wait longer. So it should be close to 5%, because this is the size, the probability of wrongly rejecting the null hypothesis. And this is the power. So when the data aren't uniform, what's the probability of rejecting the null? Well, it ranges from about 24.5% with the binomial test, but with these other tests, it goes up to about 43.5%. So we can get more power. And this is a distribution which is pretty close to uniform, but by changing the kernel, so by moving away from the binomial test, we can get more power. The question of which one to pick really rather depends. And for different examples, certain tests may be more powerful than others. And I've just picked a selection. Right. I think I have then, in that case, enough time to address the final topic, which is the conditional tests. And this will make a link to what I do next week as well. So this is the final idea. What I've just done there is I've implemented 7 different unconditional spectral backtests. They test for lack of uniformity, but in such a way that I concentrate on certain quantiles. The binomial concentrates on 99. This one looks at 3 different quantiles. This one looks at 3 different quantiles. These ones look at intervals between 95 5% and 99.5%. Now, what about the case where the risk modeling group doesn't model volatility properly? So that would be the third group. If you remember the third group, they were too lazy to really look at volatility, so they were just looking at distribution. So how do you find evidence of unmodeled volatility in pit values? Well, this is what you can look for. So we are going to, so maybe it's best to do this with R. So I'm going to generate a third set of pit values, okay? And I'll show you how I do it in a second. What we're going to find is when we draw the histogram, it looks pretty uniform. So I've called them pit 3, and I'll show you how they're constructed shortly. When we draw the histogram, it looks pretty uniform. If we look at correlations, we don't see any. But if we make a transformation of the pits, and so V pit 3, this is a very simple transformation where I take the pits and I take twice the pits minus 1, and I call that V pit 3. They still look pretty uniform, but what you find is you find lots of serial correlation. Okay, so the difference between this picture and this picture is the serial correlation. And if pit data are independent, we can't see serial correlation. Now, what is this really weird transformation, 2pt minus 1? It is a uniformity preserving transformation. If pt is uniform, then twice pt minus 1 in absolute value is also uniform. That doesn't change. But it is a transformation which reveals unmodeled volatility. And if I go to R at this point, so in the next section, we consider conditional tests. So sometimes pit data can appear uniform but hide serial dependence. So this is the way that I generate pit 3. I set a seed. That just means that I can reproduce this example. And I'm going to use a model from next week's class, which will mean nothing to you now, but I'm going to use a model and simulate actually 5,000 points from it, that model. I'll tell you about the model next week. But if I look at a histogram, those look pretty uniform. If I look at the autocorrelation function, they look uncorrelated. If I look at the autocorrelation function of the absolute values, well, that doesn't make any difference because they are positive. If I look at the time series plot, it's all between 0 and 1. But now, if I make this transformation, I take twice the pits minus 1 in absolute value. If I look at the histogram, still looks uniform, but I look at the ACF, then I see some evidence of correlation. Okay, now, how could I find this in my tests? How could I test for that? So let me go back to the slides. What we want to do is we want to test whether the weighted pits are independent of the past. And so we want to test what's called the Martingale difference property. So the weighted pits, what I'm going to do is I'm going to subtract their mean like this. So I'm just going to subtract their mean and I'm going to call it WT tilde. Under my null hypothesis, it must be the case that the expected value of WT tilde given the past is 0. Because the weighted pits, under my hypothesis, they're independent of the past. Now, for any vector which depends on the past, the expected value of the product of that vector and WT tilde should be 0. But what I'm going to do is I'm going to create a vector which depends on the past in a very explicit way. Namely, I'm going to take the h function that I've just talked about here. I'm going to take this function. So I'm going to look for a dependence on past values of this transformation of the pits. And I'm going to use a test in econometrics, which was developed by Giacomini and White. I'm not going to go into it, but it is another test where the reference distribution is chi-squared. And so in the interest of time, let me skip on to the next slide. I'm going to look at conditional spectral tests. If you know the test of Engel, who got the Nobel Prize for Gauch models, if you know the test of Engel and Manganelli, which is called the dynamic quantile test, this in fact is a generalization. And it contains the Christopherson test as a kind of, or it more or less contains it as a special case. And basically it expands on the ordinary spectral Z test by adding a test of this Martingale difference property as well. And the H function we use in the construction of the test, so when this whole test statistic here depends on y tilde depends on y depends on H depends on past pit values. And if there's no dependence on past pit values, we should not get a significant test result. But what we're going to see is that the results show that the unconditional spectral tests, are not sensitive to violations of the Martingale difference hypothesis caused by serial dependence in the pits, provided the distribution is close to uniform. But we do have some conditional tests in this framework which can detect the serial dependence. So that's the final, the next slide is my concluding slide, but I want to show you this with R. So the transformation H here, this is called a conditioning variable transformation in our framework. This is called a conditioning variable transformation. And it's the one that's applied to these past values. And it's set up in R, a little bit like the kernel. And for our tests, we need to set up a conditioning variable transformation, which can be used with a single spectrum test. And we need to set up one which can be used by a dual spectrum test. I won't go into that except to say that we will look at dependence on the last 4 days. So it could be 10 days or 20 days, but we will look at dependence on the last 4 days. That's why it says 4L here and 4L there. And we're going to run another simulation. This time it's still 200 replications. It's still the same sample sizes, but this time we will have independent uniform data and we will have dependent uniform data, and we'll reduce the list of tests. So we'll reduce the list of kernels. And so when it's independent, the data will be truly independent uniform. And when it's dependent, the data will have exactly the kind of dependency you find when volatility isn't modeled. And so we set up a simulation. We always need a single function, a do1. So I call this one do1-2 because it's the second one I've defined. And then we run a simulation. So the simulation is running, but this time I think we can look at what you will get here at the bottom. This is the final thing. So we're setting up the simulation, we're running it. What it will generate is the table at the bottom here. And what you'll see is that when the data really are independent, these tests will have a rejection rate of about 5%, which means that they have absolutely no power whatsoever to, sorry, let's put it a different way. It means that the conditional tests have the right size. It means that the conditional tests have the right size because we are using conditional tests. That's perhaps worth saying that when we use the do1 function, we use a function called Spectral MD test. So we are using these conditional tests. And the first 2 rows show you that the size is right. There's no dependence, and therefore you wouldn't expect significant results. But when there is dependence, you get very good results. You know, you get powers up to about 66% to detect this dependence. But the powers in the case of the non-binomial test are bigger. So for the binomial test, it's like 23 or 27, depending on sample size. But for the other ones, you get quite a lot more power, 49 to 66. So going beyond the VAR test also gives you more power here. Right, that's still running. While I make my concluding remarks, it will probably finish. It does. Oh, it's actually finished now. So that would be the table there that I've just shown you. And so the final thing to say is this. What I've wanted to say today is that under this fundamental review of the trading book, model validation and backtesting has become more strict, and it now also extends to desk level, so it's not just the whole trading book. Backtesting is important because it can lead to a couple of unpleasant consequences. You can get a higher multiplier if you have too many exceptions, or you can also lose internal model approval for either some desks or for the whole trading book. And so I believe that to comply with the new requirements and to anticipate further developments, it's actually a good idea to look at these tests based on realized p-values, which I would call pit values. They go beyond the binomial test. They are generally more powerful than the binomial test. You can have conditional tests, which test for serial dependence in the pits, as I've just shown you at the end. Moreover, this framework is a kind of overarching framework because it contains the binomial tests. So what I've shown you in part 3 is a framework that subsumes a lot of the standard tests and gives you more tests which are more powerful. The discrete ones, I call those multinomial exception tests, are quite simple. That's an easy extension to binomial tests. And and tests can also identify serial dependence in the pit values, which is typically caused by a failure to model the dynamics of trading book risk, that is the volatility of trading book risk. Okay, the references are found here. I'll just draw your attention to the main paper. So this is the one in the Journal of Banking and Finance, which describes the theory of spectral tests. And I did have an earlier paper with Marie Kratz, which is a special case, and that's the multinomial tests, which are a special case of the spectral tests. Apart from that, there's the reference to my textbook and some of the other things I've talked about. So I'm going to stop the share and come back into the room, and we can take questions.